Fluids under pressure perform many valuable functions in industrial applications. For example, turbines are powered by steam that's under tremendous pressure, and gases under pressure are used for welding. But if pressure becomes too great, it can cause damage and injuries. To prevent such problems, a fluid system must have a means for relieving excess pressure quickly and safely. Various devices are used for this purpose. Rupture discs are often used in systems where problems with excess pressure are relatively unlikely. Relief valves, which open gradually, are primarily used in systems that handle pressurized liquids. In gas or steam systems, however, safety valves are used. They're able to quickly let out large volumes of gas or steam to relieve excess pressure in the systems. Safety valves are commonly used on gas or steam lines because the volume of the gas or steam increases as pressure decreases, and a gas that's under pressure may expand to a tremendous volume when the pressure is relieved. One thing all safety valves have in common is that they open wide very quickly and stay open until the system pressure drops a predetermined amount below the point at which the valve is set to open. The valve allows a large volume of gas to escape as pressure is reduced. In this part, we'll look at a huddling chamber safety valve. This type of safety valve is named for a small space called a huddling chamber that's located just below the valve's disc. The valve has an adjusting ring that's used to direct escaping steam either toward or away from the disc. The valve body directs the flow of pressurized fluid. The disc and seat seal the system closed under normal pressure. The disc is mounted on a stem. A spring holds the disc in place, and the valve stem transfers tension from the spring to the disc. The release lever is used to trigger the valve manually while the system is operating to make sure that the valve works properly. The disc has a lip or shoulder that isn't exposed to system pressure when the valve is closed. The lip of the disc sits above the huddling chamber. The center portion of the disc, which is located over the valve's inlet, is always exposed to system pressure. The purpose of the huddling chamber is to help expose a greater area of the disc to escaping fluid when the valve opens slightly. The fluid pressure acting on the increased area gives a greater total lifting pressure against the spring. The pressure at which the valve's disc begins to lift off the seat is called the valve's set pressure. The pressure at which the valve actually pops open is the popping pressure. In most cases, simmering occurs briefly before a safety valve opens fully. During simmering, the disc is only slightly lifted and the valve discharges a small amount of fluid. Simmering lasts for only a fraction of a second until system pressure acts on the lip of the disc. As the disc lifts, the lip of the disc is suddenly exposed to system pressure. Since a larger area of the disc is now exposed to the pressure in the system, more force is being exerted on the bottom of the disc. This increased force overcomes the spring tension and causes the disc to pop open to about a 60% open position. When the valve's popping pressure is reached, the valve should open with a clean and sudden pop. If the pressure in the system continues to increase, the velocity of the escaping fluid will also increase, causing the disc to gradually lift higher until it reaches the fully open position. Since the initial opening of the safety valve is about 60%, a large volume of fluid is allowed to escape quickly. After the excess pressure in the system has been relieved, the system pressure will begin to drop. As pressure decreases, the velocity of the escaping fluid also decreases. Spring tension begins to take over, pushing the disc down. The spring tension in a safety valve is preset, and it must be correct for the valve to operate properly. When the system pressure drops to the point where the valve popped open, 1,000 psi in this case, the valve doesn't close, because the lip of the disc is still exposed to the pressure and velocity of the escaping fluid. When the system pressure drops to a predetermined value below the valve's popping pressure, the disc drops down on the seat, closing the valve. This predetermined value is the valve's reseating pressure. Typically, as the force of the escaping steam is lost, the valve shuts suddenly. A small cushion of steam trapped in the huddling chamber keeps the disc in the seat from slamming together hard enough to be damaged as the valve snaps shut. When the disc is firmly in place against its seat, the valve is said to have positive seating. Positive seating is important because it keeps the valve from leaking fluid through the disc and seat. The distance that a valve disc moves from the closed position to the fully open position is referred to as the valve's lift or travel. Adequate blowdown helps prevent a condition called chattering. You see, if there's no difference between a valve's popping pressure and its seating pressure, the valve disc will jump up and down on its seat until pressure either increases enough to pop the valve open again or decreases enough to keep it closed. This condition is called chattering because of the sound that the disc makes as it moves up and down. Chattering can seriously damage both the disc and the seat because it promotes steam cutting. Steam cutting occurs when the velocity and the temperature of the escaping steam are so high that the steam cuts into the metal of the valve's disc or seat. Blowdown can be adjusted by changing the setting of the valve's adjusting ring. You see, the position of the disc in a safety valve is determined by the amount of system pressure and the angle and velocity of the steam striking the disc. When the adjusting ring is in the raised position, the escaping steam is directed right at the disc. The velocity of the escaping steam exerts a great deal of upward force because most of the steam is aimed to strike the disc closer to a 90-degree angle. In turn, the system pressure must drop well below the popping pressure of the valve before the spring can force the disc back onto its seat. So raising the adjusting ring increases the blowdown of the valve. If the adjusting ring is lowered, it's easier for the steam to escape to the side of the disc, so much less escaping steam strikes the disc on its way to the valve outlet. The velocity of the steam exerts less upward force on the disc, and more system pressure is required to hold the disc open. So with the adjusting ring in the lowered position, the valve closes against higher system pressure than it did when the ring was raised. Lowering the adjusting ring, then, decreases the blowdown of the valve. In this part, we'll examine the components and operation of two specialized types of relief valves that may either function as safety valves or assist safety valves in protecting pressurized systems. The two types are safety relief valves and pilot-actuated relief valves. We'll begin with safety relief valves. While safety valves typically discharge gases or vapors, safety relief valves discharge gas, vapor, steam, or liquid to prevent a predetermined safe pressure from being exceeded. Safety relief valves are commonly used in refineries, on systems that contain liquid vapor mixtures, and in some low-pressure steam systems. Some types of safety relief valves are suitable for use as either a safety valve or a relief valve, depending on the application. For instance, certain safety relief valves can be used as safety valves on air systems and as relief valves on liquid systems. This is a cutaway illustration of one type of safety relief valve that's specifically designed for use in gas or steam systems. It has a long nozzle-shaped inlet, a disc and seat, a reaction hood for directing the flow of fluid through the valve, and a single adjusting ring for changing blowdown. The pressure of fluid directed against the disc lifts the disc off the seat. While the valve briefly simmers, the flow of the fluid as it discharges outside the valve's seating area increases the lifting force. Then, the reaction hood deflects the discharging fluid downward. Creating a reactive force by deflecting the flow of the fluid further increases the lifting force and causes the valve to pop open. As system pressure returns to normal, the valve closes. This is a pilot-actuated relief valve. It may also be referred to by any of these other names. Pilot-actuated relief valves operate much like safety valves. That is, they pop open rather than open gradually, and they have a predetermined amount of blowdown to prevent chattering. However, a pilot-actuated relief valve also has a separate pilot device that senses excess pressure conditions and causes the valve to open. This arrangement allows excess pressure to be detected in one part of a system, such as a steam line, while the valve protects another part of the system, such as the boiler. Pilot-actuated relief valves are often used on gas and steam systems that also use safety valves. In such cases, the pilot-actuated relief valves are set to open at lower system pressures than the safety valves are. This arrangement saves wear and tear on the safety valves and prevents costly shutdowns that would be required for safety valve repairs. You see, by law, safety valves can't be isolated from the systems that they protect because of the damage that could occur if the systems were operated without protection. So, whenever a safety valve is damaged, its system must be shut down while repairs are made. Pilot-actuated relief valves, however, can be isolated from a system because they're not a primary part of the system safeguards. So, the pilot-actuated relief valves can be used and then repaired if necessary without having to shut down the system. The disc opens downward, allowing the steam to escape through the outlet at the upper part of the valve body. Also, in this example, the spring is placed below the disc. The valve also has a disc guide, which is a sleeve that aligns the disc with the seat. A small opening between the disc guide and the disc allows system fluid to pass through from the inlet to the bottom of the main disc. Consequently, system pressure is exerted on both the top and the bottom of the disc during normal system operation. Spring tension is also exerted on the bottom of the disc. If system pressure increases, it increases on both sides of the disc, but the valve won't open because the pressure on the top of the disc counterbalances the pressure on the bottom, and spring tension holds the valve closed. The pilot device initiates the valve's opening. The device is set to open at a predetermined pressure. A pressure-sensing tube in the pilot device detects increases in system pressure, and when system pressure reaches the predetermined level, the pressure-sensing tube activates an electrical relay. The electrical relay closes an electrical circuit and energizes a solenoid. The solenoid then lifts a pilot valve, and the excess pressure is relieved. The excess pressure that's relieved by the pilot valve comes from below the disc in the main valve. The amount of pressure that the pilot valve is capable of relieving is greater than the amount that could leak between the disc and the disc guide. When this pressure is relieved, the only pressure that remains on the disc is the pressure that's above it. With no counterbalancing pressure below the disc, the pressure above the disc easily overcomes the spring tension, so the valve opens to release system fluid through the outlet above the disc. When system pressure returns to normal, the pilot valve closes. Pressure then builds up again below the main valve disc and helps the spring hold the disc closed. External inspections of safety valves are conducted when a problem is suspected, and also when routine preventive maintenance or testing is scheduled. In this part, we'll see a typical external inspection, and we'll look at hand lifting a valve when the external inspection indicates that certain problems may be present. In preparation for an external inspection, check the operating history of the valve. This will give you an idea of specific problems that you should watch out for during the inspection. Next, proceed with a step-by-step external examination of the different parts of the valve. For this 2-ring huddling chamber safety valve, first check the lock wire on the adjusting ring pins. The lock wire is fastened in place with a metal clip as the final step in the valve reassembly procedure. So the presence of the metal clip is a sign that the adjusting rings should still be properly set for operation. If the metal clip is missing, or if the lock wire has been tampered with, the valve set points may not be correct. Then you must have the valve taken to the shop to check the adjusting ring positions, and if necessary, reset them.